When you see this line of code, what do you think it does? Most developers would surely answer, allocate 4 bytes of memory, write the value 42, end of story. But the truth is far from that simple. Behind the single line of code lie 5 layers of low-level C++ mechanisms. And most developers even misunderstand the first key point. New is not a function. New is a C++ keyword expression, not an ordinary function. The essential difference between the two is a function is a single-purpose code encapsulation. For example, malloc only allocates memory. Ester copy only copies strings, whereas an expression is a predefined language-level execution sequence that triggers a series of related operations and is strictly constrained by the language standard. When a developer writes a new expression, what is triggered is not a simple API call for memory allocation, but the complete process defined by the C++ language specification, including memory acquisition, object construction, alignment guarantees, exception handling, and several other critical steps. Most developers only see the superficial memory allocation behavior and overlook the C++ object lifecycle management logic that lies behind it. For this line of code, the execution flow of the new expression can be broken down into the following 5 key stages. The first step of new is to call the global operator new function to obtain raw memory. The core responsibility of this function is to allocate uninitialized raw memory from the system heap, sized according to the target type. In the default implementation of the C++ standard library, operator new is typically implemented via malloc underneath. But developers can completely replace the default logic with custom allocators. For example, using tcmalloc, Google's open source allocator optimized for multi-threaded memory allocation, or gmalloc, the default allocator in FreeBSD, known for low fragmentation in high-performance server scenarios, or a minimalistic allocator in embedded systems. The key point is that we can overload operator new to take full control of the memory allocation logic. For example, in high-performance scenarios, we can implement custom allocation strategies such as memory pools or allocation statistics by overloading operator new. All new expressions reuse that allocation strategy, thus achieving flexible customization of the memory allocation mechanism. After memory allocation is complete, new performs an alignment check and adjustment, an easily overlooked but critical step. Every data type in C++ has a specific alignment requirement. For example, int by default requires 4-byte alignment, double requires 8-byte alignment, and user-defined types can specify stricter alignment using the align as keyword. Why is alignment necessary? Misaligned memory access causes 2 major problems. First, performance penalty. The CPU reads memory in units called cache lines, typically 64 bytes. Misaligned data requires 2 separate reads and a reassembly, drastically reducing efficiency. Second, compatibility risk. On architectures like ARM and RISC-V, misaligned memory access directly triggers a bus error and crashes the program. If the initially allocated memory address does not satisfy the alignment requirement of the target type, the new expression automatically allocates a small amount of extra memory, at most the alignment value of the target type, and adjusts the address by an offset to achieve proper alignment. This leads to a key conclusion. The actual amount of memory allocated may be larger than what the developer requested. For example, when you request 4 bytes for an int, if the initial address is not 4-byte aligned, new will adjust it. At that point, the actual allocation is 8 bytes, with the extra 4 bytes used to guarantee alignment. This redundant memory is transparently managed by the compiler. The developer does not need to be aware of it. Memory alignment is a low-level design in C++ that ensures cross-platform compatibility and runtime efficiency, and it is an important feature that distinguishes C++ from C, which did not strictly enforce alignment in its early days. After memory alignment is complete, we reach the core of the new expression, object construction. This is the essential difference between new and malloc, and it marks the boundary of responsibility between operator new and the constructor. Operator new and the constructor are completely independent components. Malloc only allocates memory and performs no initialization. Operator new has a wrapper around memory allocation, likewise produces only a black block of memory. The constructor's sole purpose is to initialize the object on the properly aligned memory provided by operator new. For built-in primitive types like int, value initialization is performed, writing 42 into the memory. For user-defined types, the constructor is automatically invoked to initialize member variables and acquire resources. By way of analogy, operator new is responsible for finding the land, while the constructor is responsible for building the house. The two work independently to create the object. The clearest illustration of this division of labor is placement new, which allows us to skip the memory allocation step and directly call a constructor on existing properly aligned memory. That line of code clearly proves the core of the new expression is object construction. Memory allocation is only a prerequisite. Without memory, you cannot construct an object, but having memory does not mean you have an object. After the object is constructed, the new expression performs a hidden operation. It implicitly records critical metadata. This metadata, though invisible, directly determines the correctness of the subsequent delete operation. The content of the metadata varies by scenario. Array scenario, the core metadata is the array length. New allocates an extra 4 or 8 bytes of memory to store the array length. This metadata area is typically located just before the array's data area. When delete array function is executed, the system first reads that metadata to determine how many destructors need to be called, then releases the entire memory block. Single object scenario. Some compilers record metadata such as size of the memory block or type identifier of the object, used for memory leak detection and debugging. This metadata is usually stored at the head or tail of the memory block and does not occupy the object's own memory space. The importance of metadata is especially evident for arrays of user-defined types. If metadata were missing, delete would not know the array length, would call the destructor only once, and the internal heap memory of the remaining 4 string objects would never be freed, causing a severe memory leak. This is the fundamental reason why arrays must be freed with delete array function. The final step is exception handling. When memory allocation fails, the default behavior of the new expression is fundamentally different from that of malloc. Malloc returns a null pointer on failure, requiring the developer to manually check. The default behavior of new is to throw a std bad alloc exception, or a derived exception, forcing the developer to handle the allocation failure scenario. If you need to avoid exceptions, you can use the no-throw version. In that case, allocation failure returns null pointer, but that is a special case. The standard behavior of new is to guarantee error detectability via exceptions. New and delete are paired management mechanisms in C++. Delete is also a keyword expression, and its execution logic is completely symmetric to that of new, with essential differences from free. For a single object, delete first calls the destructor of the object pointed to by P, destroying the object and releasing its internal resources. Then it calls operator delete to release the underlying memory. For an array object, delete array function first reads the metadata to obtain the array length. Then it calls the destructor for each element from the end of the array to the beginning, avoiding order-dependent errors. Finally, it calls operator delete array function to release the entire memory block. The essential difference between delete and free is that free is a C library function. Its only role is releasing memory. It does not involve any object-related operations. Delete, in contrast, recognizes the object first, then the memory. It must be used on a valid object created by new. It first destroys the object semantically via the destructor, then frees the memory. Returning to the original code, we can now fully articulate its execution logic. Memory allocation to alignment handling, to object construction, to metadata recording, to exception handling. These 5 stages are interlocked and together form the complete execution flow of the new expression. If you found this content insightful, feel free to like, follow, and share. See you in the next video.